All right. So, example 3 here is where we left off. Okay, if you remember yesterday we went through a very long process, okay, of kind of describing how behaviors of f, right, relate to then behaviors of f prime and behaviors of f double prime as well. Okay, and specifically how we can use the graph of f prime to then interpret information about f and also interpret information about f double prime, okay, and stuff like that. All right, so we're looking visually now, okay? We spent a lot of time up to this point looking kind of analytically at things because we would just, have a function, take its derivative, take its second derivative, find, relative extrema, find points of concavity, find points of inflection, find intervals of concavity and intervals of increasing and decreasing, all that stuff. But now we're talking about using it by visually kind of seeing the information before us and then interpreting it just from the graph, right? And so we did that here. We just kind of assume this is the graph. We started with assuming this is the graph of f of x and then identified different pieces of information just from looking at it, okay? And then we started to assume that same graph now is f prime, and we answered some questions here based off of that using our little, I guess table or chart or, wall of information there. All right, and so now we'll take a look here at example 3, which you all have started on already. We are given the function in this situation, so it's kind of like going backwards a little bit to what we have done before, something that we're more comfortable with. And so we're asked to find the intervals increasing, decreasing, concave up, concave down, relative max, relative min, and points of inflection. So this is going to involve kind of like a full analysis, we can think, So I'll go ahead and take that first derivative there. Again, most of you guys, I think, got started on it at least yesterday. So I'm just going to jump right in and just do it here. Okay, so we have f prime of x then is equal to x squared minus 4, which when we set that equal to 0, to find our critical points, we get x equals plus or minus 2. Okay, and so we have then for our number line for f prime, we're going to put negative 2 and 2 on there. Okay, and then we'll just plug in some points. So like negative 3 squared is 9, minus 4 is going to be positive. 0 squared is 0, minus 4 will be negative. And then 3 maybe we'll say, again, 9 squared is positive. So there's our intervals, okay? So for f is increasing, okay, f is increasing when our first derivative is what? Positive. So increasing from negative infinity to negative 2, union 2 to infinity, right? And then f is decreasing when f prime is negative, so that's from negative 2 to 2. Okay. We can also identify relative extrema here. Relative minimum of, of f at x equals what? What does our analysis here tell us? X equals 2, right? Because the first derivative is changing from negative to positive. Okay, and we have a relative maximum of f where? At negative 2, right? Because the first derivative is changing from positive to negative there. So the original function would be changing from increasing to decreasing, right? Increasing to decreasing, decreasing to increasing. So you can indicate those if you want in there, just kind of help you. All right, so that is kind of all the information we can kind of pull using our first derivative, but now we need to also determine concavity and points of inflection. And what do we use to help us determine concavity and points of inflection of a function f? What do we look at? Second derivative, so f prime prime of x equals 2x. Set it equal to 0 for our critical points. We also, of course, whenever we find critical points, we want to set the derivative equal to 0 or when it would be not exist. But of course, in either of these situations, the derivative will always exist. So it's really just setting the derivative equal to 0 there. So we get x equals 0. And so we'll make our little number line here. That's kind of nice. Okay, for f prime prime, we'll check to the left of 0. To the left of 0, we use negative 1. 2 times negative 1 is negative 2, so it's negative on that interval. And to the right of 0, 1. 2 times 1 is positive 1, so it's positive on the interval. So f is concave up. F is concave up when f prime prime is positive. So in this case, is 0 to infinity. And f concave down like a frown, from negative infinity to 0 when that second derivative is negative. And do we have any points of inflection? Yes. Where? Okay, f has a point of inflection at x equals 0 because, how did we know that f had a point of inflection at x equals 0? The concavity changes. Okay, so yeah, I would say given this information, we can say that f will have a point of inflection because f prime prime changes from negative to positive at this point, meaning, if you want then to extend onto that, meaning that f changes from concave down to concave up at that point. Okay? So the purpose of this was to take all this information and to kind of see it happening here, and then also kind of see it happening here as well, right? So let's take a look at this. Right? Okay, so we're saying that f is increasing from negative infinity to negative 2. So negative infinity to negative 2, certainly our graph is increasing, and also 2 to infinity there. We can see it as well. Right? We're also saying that we have a relative minimum of f at x equals 2, and certainly at 2 we do have a relative minimum there, a little valley, right? And at x equals negative 2 we have a relative maximum, a hill. Looks good. Okay. F is concave up from 0 to infinity. Okay, concave up. Remember, we have really two ways of thinking about concave up. One way to think about concave up is the fact that it looks like a cup, right? It looks like a cup. The shape of the graph is like a cup. But another way to think about it too is that, bless you, if you were to graph a tangent line to any point of the graph in this interval here, the graph would be above the tangent line, right? Any tangent line that you drew in this interval from 0 to infinity where f is concave up, where f is concave up, any tangent line you drew, the function would be above the tangent line. Whereas, if we looked at the concave down intervals, okay, the function would be below any tangent line in this interval. Okay? So if the function's above the tangent line, concave up. If the function's below the tangent line, concave down. It's another way to see that, okay? You can just kind of imagine drawing tangent lines, in here kind of thing. And in all those situations, the graph would be below the tangent line, so that's concave down. In all these situations, all the tangent lines you would draw here would be, the graph would be above the tangent line, so concave up for that interval too. That's a different way to think about concavity. If you maybe have a trouble, seeing the frown or seeing the cup there, that's another way to think about it. Okay, and then of course at 0, right, we are changing from that concave down to concave up behavior, and so point of inflection there at 0. Okay, but let's see how these things also show up then in our first derivative, right? This is y prime. Okay, so we also want to be comfortable seeing these things showing up in y prime. Okay, so where f is increasing, we know our first derivative is positive. So negative infinity to negative 2, 2 to infinity, there it is, right? Our first derivative, negative infinity to negative 2, y prime is positive, and y prime is positive here, indicating the function will be increasing. From negative 2 to 2, y prime is negative. So therefore, the original function will be decreasing on that interval. So there's that. Okay? We can also see our relative minimum too. The relative minimum occurs when the derivative changes from negative to positive. So from negative, there's our first derivative when it's negative, to positive at 2, we have a relative minimum. And sure enough, at 2, there's that relative minimum, okay, of f, or the original function y, I guess I'll say. Okay? Likewise, where our derivative changes from positive to negative, then that indicates a relative maximum. And certainly at negative 2, there's our relative maximum right there. Okay? We can also talk about concavity as well. Okay? Where y prime is increasing, its derivative, y prime prime, will be positive, and so therefore the original function will be concave up. So 0 to infinity, our function y prime is increasing, so therefore the original function will be concave up, and y prime is decreasing from negative infinity to 0, indicating its derivative, y prime prime, will be negative because we're decreasing. Okay? All those tangent slopes are going to be negative. And so therefore the original function will be concave down on this interval. And certainly it is, right? Certainly it is. And then finally, point of inflection, well, that's your relative min here. Your relative extrema of the first derivative will be points of inflection in the original function, okay, or what you get from the second derivative there. Okay? So that relative min becomes a point of inflection. All right? That's perhaps the trickiest thing, right? That's what our ultimate goal is here, right? Hopefully seeing this here and then being able to see it here, that's hopefully super, straightforward for us, pretty easy. Maybe concavity, we're still having a little bit of trouble. But the biggest challenge, right, is being able to use this graph and being able to pull the information from here to then talk about this, right? Seeing this also show up in here, or using this to be able to see this information, right? That's what we really ultimately, our goal is for this section, okay? So we'll practice that a little bit more because we've got more problems. All right, so now moving into these examples, these are more kind of typical AP style questions right here, okay? So this is what you can see. Some of these are pulled straight from like old tests, like free response questions, okay? Some of them maybe will show up as multiple choice, kind of thing. You can, but they are a very typical style of AP questioning, okay? So we want to be super comfortable with this. All right, so graph of f prime is given to us here with some pieces of information. Super important here, folks. I'm gonna say this. Some of you maybe still will, get caught up in things. But I'm gonna say it anyway, just to make sure I can, at least give you the try here. So you want to read this information here. I know that seems kind of silly, but you want to read it. Rarely is there a piece of information given in here that you will not use. So very rarely is there some sort of red herring they throw in there that doesn't really mean anything or isn't necessary. Most of the time, every bit of information here you will use at some point through your letters here. So please make sure that you read all this information, especially if you see something that's like, well, that's odd that they would give that piece of information. That will most likely be used at some point later on. If you don't use that weird side piece of information, the chances are you missed something. Okay, so keep that in mind too. All right, let's read through this. The figure above shows the graph of f prime. Duh, it says it right there. The derivative of the function f. Duh, that's what f prime means. On the closed interval from -1 to 5. Okay, yeah, -1 to 5 right there. Okay. The graph of f prime has horizontal tangent lines at x equals 1 and x equals 3. Okay, so all that's telling us right there is that 1 and 3, they look like they are relative extrema, and in fact they are relative extrema because of the fact that we're told f prime has horizontal tangent lines. Sometimes they'll tell you this, sometimes they'll expect you just to be able to see, aha, that looks like the low point right there, that looks like the high point of the hill or the low point of the valley there. So whatever there. The function f is twice differentiable. Okay, that's important too, right? F, not f prime, but f is twice differentiable, which means f prime is continuous, right? And f prime prime is continuous. With f of 2 equals 6. So there's that like little weird piece of information. You're like, well, that's weird. Why are they telling us that f of 2 equals 6 when we're given the graph of f prime here? But that will show up later. So I'm going to, kind of like underline that for right now. That'll come up here in a second. Okay. So question A asks, it asks us to find the x coordinate of each of the points of inflection of the graph of f. Give a reason for your answer. Okay. So if we want to find points of inflection of f, but all we have is f prime here, how do we do that? Well, let's go back to our little chart here to help us, kind of remember. Maybe we don't have it quite down yet. If we want to find points of inflection, a function f has a point of inflection when, if the graph shown as f prime, the point of inflection will be either a relative maximum or relative minimum. Okay, so that's crucial right there. So we go back to our graph. Okay. Looking at the graph of f prime here, do we have any relative maximums or relative minimums? Yes. Where? 1 and 3, right? We don't need to differentiate between the two. It doesn't matter that 1 is a relative max and 3 is a relative minimum. It's just there are relative extrema here at 1 and 3, and so those will be points of inflection of the graph of f. Okay? So we will identify those at x equals 1 and x equals 3, f will have a point of inflection. If you can get to that point, you've partially answered the question correct, and you've earned yourself some points there, okay? So it's not necessary that you answer the full question, right? If you can get to this point, you've answered part of the question, you will get some points. All right, that's great, but of course, we're not done yet because what do we still need to do? Give a reason or explain. Exactly right. Okay? So the explanation for this can be something as simple as, well, this, and I'm going to actually, let me not finish my sentence there. I'll say because f prime changes, okay, And again, we pulled these out because they are relative extrema, right? 1 is a relative maximum, 3 is a relative minimum. But what indicates that we have a relative maximum and relative minimum there? Well, f prime is changing. F prime changes from increasing to decreasing, or vice versa, we'll say, or decreasing to increasing if you want to be more complete and not use vice versa. So from increasing to decreasing, or vice versa, at these points. Okay? And I think that's sufficient. I do think that is sufficient there. That's all we really need to say. Okay? If we wanted to go further, we can then say, therefore, and maybe I'll do that here just in this one case. Therefore, and it's fun to use therefore, right? So therefore, f prime prime changes from positive to negative, or vice versa. And thus f changes from concave up to concave down, or vice versa, at these points. Okay? I know that's a lot. Okay? And I think that is a little bit overkill. Like I said, I think we could have stopped after the first sentence there. Okay? But this is not a wrong chain of reasoning, right? Since we know that f changes from increasing, f prime is changing from increasing to decreasing, therefore its derivative, f prime prime, will change from positive to negative, or vice versa, at those points. And thus f will be changing from concave up to concave down. Okay? So that is literally, reasoning from what we're given to what we're trying to show, right? We are reasoning from what we're given, kind of like a proof, right? We start with our given information, and then we reason to the point that we're trying to show here. Okay? So that's the idea there. Again, do you need this? No, I really do think the first sentence there is sufficient, but it can't hurt, to show you guys the rest of that. I won't do it for the rest of the explanations, though, like that much. Okay? Questions on A? Okay, so letter B, is f of 4 less than 6? Justify your response. Okay. Is f of 4 less than 6? Justify your response. So, what do we know about f? F of 2 equals 6. And this is where we're going to use that little weird piece of information that we were given here. So we're told that f of 2 is 6, but we're not interested in f of 2. We want to find out if f of 4 is less than 6. We know at f of 2, the function is 6. But how can we use that piece of information in this graph here to determine if f of 4 is less than 6? Matthias? Okay. Okay. From 2 to 4, you're saying f is increasing? Well, now, if you take a look here, be careful. This is a graph of f prime. What is the sign of f prime from 2 to 4? It's negative, therefore the original function will be decreasing. So, will f of 4 be less than 6? Yes, it will be. Okay. So right reasoning, just a little twist there. Yep, but that's the right kind of thinking there. So good job, very good. Okay. So let's see here. We'll say f prime is negative from x equals 2 to x equals 4, not including 4. Okay, I'm going to try to draw a line here to not get those confused. Okay, f prime is negative from x equals 2 to x equals 4. Therefore, f will be what? Decreasing. So f is decreasing on that interval. Okay? Since f of 2 equals 6, then f of 4 must be less than 6. Okay. Is this the only way to say this? No. Is there a better way to say it? Maybe. Okay. But I think that hits all the important pieces of information. Starting with information that we already have, both from the words up here and from the graph, and then reasoning towards what we're trying to conclude or justify. That f of 4 must be less than 6. I think that's pretty sufficient. Okay? Okay. Letter C. At what value of x does f attain its absolute minimum value on the closed interval from -1 to 5? Okay? Show the analysis that leads to your answer. Okay. So, absolute extrema, in this case the absolute minimum value, notice we're not asked to find what the absolute minimum value is, right? So we're not trying to find the y value that is the lowest of f. We're just trying to find at what x value, where does the absolute minimum occur, okay? Well, this is where knowing your fundamentals is helpful, right? How do we even find absolute extrema? What do we normally do? The endpoints of the interval, and also where the derivative is what? 0 or does not exist, right? So it's essentially our critical points and our endpoints of our interval. Okay, looking at the graph f prime here, do we know what the endpoints of our interval are? Yeah. What? 5 and -1, -1 to 5, right? Okay, so we've got those. Do we know the critical points of f by looking at f prime here? Yes. Yes, where are they? 1 and 4, very good. Okay, again, looking at the graph, where is f prime equal to 0? 1 and 4. So we have 4 candidates. We have 4 candidates that we must, kind of reason about and determine from those 4 which one of those is the absolute minimum value. Okay? So, I'm going to establish that here. There are 4 candidates for absolute minimum of f. The endpoints of the interval, and the critical points, x equals 1 and x equals 4. Okay, there are 4 candidates for the absolute minimum of f, the endpoints of the interval, which I think that you see there, and the critical points, x equals 1 and x equals 4. Maybe I'll throw those in here. The endpoints of the interval, x equals -1, x equals 5. Okay? So let's kind of consider these things in order. All right? So, at x equals -1, okay, so at x equals -1, I got to bump back up here, okay? F prime, what is the sign of f prime immediately after -1? F prime is negative, therefore f will be what? Decreasing. So, can -1 be the location of an absolute minimum if in our function we are decreasing immediately to the right? If you have a point, right, and you start decreasing immediately to the right of it, there's no way that point can be an absolute minimum, right? In fact, it might be the absolute maximum, potentially there, depending on the scenario. All right, so at x equals -1, f prime is negative to the right. So f is decreasing. Thus, x equals -1 cannot be the absolute min. Okay. All right, candidate number 2. X equals 1. All right, so I guess I'll leave that up there. Okay. So looking at x equals 1, okay, in our graph f prime here, what happens immediately to the right of x equals 1? F prime is what? negative. So therefore, f will be decreasing. So the same is true for x equals 1. Okay. At x equals 4, what behavior do we observe there? To the left of 4, the derivative is what? To the right of 4, the derivative is positive. Which indicates what? A relative minimum. Okay, a relative minimum. And since we increase up to the 5 there, right, since the derivative f prime is positive up to the 5, x equals 4. Whoops. Since f prime is positive between 4 and 5 there, 5 will be higher than 4. X equals 5, or f of 5 will be higher than f of 4. So 4 must be the absolute minimum. Okay, so I'm going to say x equals 4, the absolute minimum occurs because from 4 to 5, f prime is positive. So f is increasing on 4, 5. F of 4 will be less than f of 5. Okay. So something like that. Again, not super succinct, but it does kind of provide a full analysis there, I would say. Because again, you want to kind of show that you're considering each one of those each one of the points, the endpoints of the interval, and those critical points, and then kind of making an argument from there. Okay. Okay. So that's kind of the idea. Questions on letter C there? Right. So D, let G be the function defined by g of x equals x times f of x. Find an equation for the line tangent to the graph of G at x equals 2. Okay, so again, this is a scenario where we've got like a bit of a weird situation here, this new function g that shows up, which is equal to x times f of x, and we want to find the equation of a tangent line to the graph of g at x equals 2. So we don't know a whole bunch about f, we know even less about g, but even with that little bit of information there, we can write the equation of a tangent line to the graph of g at x equals 2. And again, it's our fundamentals that will guide us here. How do we write the equation of a tangent line? What do we need? We need to use the derivative to find the what? Slope, and also a y value, a point. Okay, so let's go ahead and do the derivative first, because this is calculus and that's what we do. So we'll take the derivative of g prime, the derivative of g, which is g prime. Okay. When I go to take the derivative of this right-hand side here, what do we need to use? It is a product, exactly right. So it'll be f times the derivative of x, which is 1, plus x times the derivative of f, which is f prime of x. Okay, so we've got the derivative of g. Now, how do we use that to find the slope? What do we do? Plug in. We're going to plug in 2. Yeah, just plug in 2. So g prime of 2. We're going to evaluate g prime at 2. We want the slope at 2. So we'll do f of 2 times 1 plus 2 times f prime of 2. Okay, just replace the x values over 2. What's f of 2? 6. Remember, we were told that way back up here. What's f prime of 2? Very good. In the graph of f prime, f of 2 is -1. Exactly right. So we get g prime of 2 is equal to 4. All right, we got our slope. There's our slope. But like some of you guys said, we also need to find the matching y-coordinate. How do we find the y-coordinate that matches to x equals 2? Where do we plug that into? Back into the original function g. So g of 2 is equal to 2 times f of 2. And what was f of 2 again? 6, we were told that. So it's 12. And so we have the point 2 comma 12. And there's our slope. And so y minus 12 equals m times x minus 2. And there's your equation for your tangent line. It is not uncommon for free response questions such as these to kind of like do like a weird kind of like tangential turn or something like that, okay? You know, here ABC, it's kind of like, okay, we're all kind of like using a similar thing. We're observing behaviors of the function. And then letter D, you know, kind of like a sudden turn where it's like, oh, now find the equation of the tangent line, okay? So another like little thing I want to encourage you is that I guess, 4 or 2 or whatever to do or whatever. If you see A, B, and C, you know, you look at those and you're like, ooh, I'm not really sure. You know, consider letter D still, right? Sometimes they're like completely different and you can still like maybe do those even though maybe you weren't sure about A, B, and C. These don't always follow one from the other. So please make sure you consider all the parts before you know, kind of give up on a problem or something like that. Okay? All right, number 5, similar situation here. So I'm going to give you guys about 5 minutes or so, 3 minutes maybe because this is time. But go ahead, read through this, okay? See what you can come up with. Here for A, B, C, and D, okay? Get as far as you can. So maybe I'll give you a few more minutes than 3 minutes, okay? But at least read through it and consider some of these questions, okay? At least try to answer them. Maybe don't worry so much about the justification. At least try and answer them, and then we can worry about, you know, finessing the justification out. Or at least try and answer these. Again, we're given a graph of f prime here. Okay? So give these a try. Yeah, if you want to talk to your neighbor or ask them a question or something like that, feel free to. That's fine. Maybe I'll walk around. With this, though.
So like, there's only one relative.
Correct. Okay, makes sense. So yeah, when we did the absolute extrema, that we have to like justify the intervals, or sorry, sim was interval and yeah. Correct. That's 5 because the curve is positive. take one more minute here, and then we'll go over the answers again. If you don't have the justifications down, that's cool. All right, we'll worry about the justifications here in a second. But at least try and get the answers down. And also try the justifications if you got the answers, okay? Try the justifications. Yes?
C. Is this like a good justification I was getting ready to say since there are horizontal tangents at x equals -3, x equals 2, and x equals 5? That means that the derivative of f prime would be 0, which means that f prime prime would be 0.
We want it to be. We want to know when it's less than 0.
Oh.
What are the intervals where it's less than 0? Yeah, just think about like the same kind of evaluation that you do. What do we normally do when we want to find relative min-maxes? We find our critical points. That's when the derivative is 0, so there, there, and there. And then you check to see the sign in the intervals between the critical points. Is the derivative positive or negative? So in this interval, the derivative is positive, so we're just switching from positive to then negative. So positive to negative means relative max. And then negative to positive becomes relative min. And then positive to positive doesn't switch, so that's neither. Or vice versa, it's become a relative extrema.
I'm trying to find an interval then.
The intervals where it's
So like, where it's like -7 to 3.
negative 3. So the
And
answer
then 2 to 5.
very good. Exactly right. Good job, Clayton. All right, let's take a look. Okay, there are the answers. At least I hope so. Goodness gracious. But anyway, yes. All right. Sorry, those are the, you know, the I guess not the justifications though, but just like the locations. Okay. Questions on any of those? So yes, Morgan. Letter D. Okay, we'll talk about letter D here in just a second. All right, because I want to get to the justifications too. So all right, so hopefully we were able to identify the letter A was x equals -1. What would be our justification here? Because f prime what? Changes from negative to positive at that point. Again, I believe that is sufficient. If you wanted to go the extra step to actually completely reason it from what we're given to what we are, trying to justify, you could say, therefore, f is changing from decreasing to increasing at that point, and so it's got to be a relative minimum. Okay, but this is sufficient. All right. All right. X equals -5. Why is that a relative max? Because f prime what? Yep. F prime changes from positive to negative. At that point. Okay. Letter C, no justification is necessary there. Right? Doesn't say justify. All right. What were we looking for here, though, for letter C? In our graph. Intervals of decreasing. Instead of asking this question, instead of saying f prime prime of x is less than 0, what words could they have used there? What behavior is this indicating of f? When f prime prime is less than 0, what does that tell us about f? Concave downward. So in other words, we could have asked find all values of x for -7 less than x less than 7, at which f is concave downward. Same question. Okay? Same question. In fact, that is a common kind of question that's being asked there. F is concave downward and f prime prime is less than 0. When is f prime prime less than 0? When f prime is decreasing. Okay? So, perhaps the most difficult analysis to do is when you're given the graph of f prime and asked to figure out when f is concave downward, just because there's more leaps in reasoning that you have to take. Okay? And then finally, letter D, at which value of x for negative 7 less than equal to x less than equal to 7 does f attain its absolute maximum justify your answer? So Morgan, this was where you had your question. Did you have a different answer that you really thought was right, or you just weren't sure how to go about figuring this one out?
Well, I thought you said that, like, to be relative or minimum, but I guess there's a difference between absolute and relative.
Exactly.
Okay, so that's right.
Yes. Right. So again, what are our candidates? What are our candidates for absolute extrema? Endpoints to your intervals. So in this case, negative 7 and 7, right? And then the critical points. So that would be the 5, the negative 1, and the 5 there. Or the negative 5, the negative 1, and the 5 there. Okay? So we have 5 candidates here. Okay? And so then the justification, yep.
How would we know that, I originally put like x equals 5 as one of my critical points, but like, do we know that it touches 0? So I like looked at that and I didn't know if they were trying to trick me, like.
I see what you're saying. We don't know. We don't know, but I will also argue then, like, we also don't know for sure that the graph is going through negative 1 or going through at negative 5. It could be like negative 4.999. So at some point we have to be comfortable with the interpretation. I mean, I'm glad that you are trying to be like, precise and consistent and stuff like that. Since they're not telling us the information, I think it's okay to assume it for these situations because we would need those otherwise, yeah.
Would we have to look at x equals 3 since
X equals 3 as a critical point. Oh, thank you. Yes, that is true. I didn't even think about that. Yes, x equals 3 is our critical point there. Yes, so let me think about that now. This might change things. So let me back up though. So that is a critical point of the second derivative. The second derivative, right? Because it is in so I guess let me see here. Critical points of f are when f prime is 0 or does not exist, right? This is f prime. F prime is 0 at negative 5, negative 1, and 5, and it never does not exist. The derivative of this, f prime prime, okay, will have critical points at negative 3, 2, because that's where we have a horizontal tangent, 5, horizontal tangent there, and at 3 because you're going to have the vertical tangent. Okay? But in this situation that we're talking about right now for absolute extrema and stuff, the critical points are where this graph will be 0 or the endpoints of the interval there. Okay. So the justification here, I'm going to hold off on actually writing out because we really need integral calculus to help us out with like the justification, with a good justification here. So I'll just kind of like argue it and then we'll worry about the full justification for a problem like this later. Okay, because you kind of need the other branch of calculus that we'll be studying here next unit actually. So for now, let me just give it to you in a basic kind of understanding here. Okay, so negative 7 is our first possible candidate, right? Can negative 7 be the absolute maximum? No, because f prime is what after negative 7? F prime is decreasing, but more importantly, f prime is positive, meaning therefore f will be what? If f prime is positive, f is increasing. So from negative 7 to negative 5, f will be increasing. So negative 5 will be higher, okay, greater than negative 7, or f of negative 5 will be greater than f of negative 7. Now, from f of negative 5, we go to f of negative 1. Okay, will f of negative 1 be higher or lower than f of negative 5? Lower, because f prime is negative between those two, so the f is decreasing from negative 5 to negative 1. Okay, so right now it looks like negative 5 is our highest point. We increase from negative 7 to get to negative 5. We decrease after negative 5 to get to negative 1. But then after negative 1, what happens? We increase for the entire interval up to 5. So now the question is negative 5 higher or is 5 higher? What do you guys think? I mean, of course, I gave you the answer is 7 here, but let's just look at these two. Is negative 5 higher or is 5 going to be higher? We decrease from negative 5 to negative 1, but we increase from negative 1 to 5. What do you think is going to be higher there, negative 5 or 5? There's not really a super good answer here, but I think there's a better answer. So, Sean? You're right for the most part. With what you guys know for now, yes, we don't quite have enough information. But does anyone have any intuition?
I think that 5 looks like it's going to be higher.
Okay, what would your argument be?
from -5 to -1, you're only decreasing for 4x values.
Okay.
You're also decreasing less.
Okay, so how do you know you're decreasing less? What's kind of indicating that to you?
The slope goes down, like, I'm not sure how to put it into words.
Okay, but I mean, do you guys kind of see what Steven's saying? He's not wrong with what he's saying. So, like, the amount that we're decreasing by from -5 to -1 is like this curve, versus the amount that we're increasing from -1 to 5 is this curve. Which one looks like a greater amount, right? Certainly the one from -1 to 5, right? That looks like more increasing than that decreasing there. And in fact, that is correct. And the way it actually works out, it's the area under the curve, okay? The amount that you are decreasing from -5 to -1 is exactly the same as the area underneath this curve, or between the curve and the x-axis here, versus the amount that you're increasing from -1 to 5 is the exact area of this space right here from -1 to 5. So under the curve, but above the x-axis there. Okay, that is integral calculus, so don't worry if that's like kind of blowing your mind a little bit here right now. We're talking about area under a curve. We will see more of that later. Okay, but suffice to say, Stephen's argument is on the right track there. Okay, we are decreasing here, but we are increasing by much more here. So 5 will be higher than f of -5. So this is our new candidate. But of course, what happens after 5? Our derivative is still positive. Therefore, f will still be what? Increasing, and so 7 then will be the highest point. Okay. But again, we don't quite have enough for the justification there, so I'm going to hold off on it, except for I just did it in lots of word vomit that you hopefully absorbed somewhat. Anyway, moving on to the next one. Okay, so Morgan, does that kind of answer your question? Okay, cool. 15 minutes later. All right, so anyway, so example 6. The function f is continuous on the closed interval. So now we're still given like a picture here, except it's a graph or a table instead of a graph. Okay, we're told that f is continuous on the closed interval -3 to 3. Again, please read this information, folks. Don't just like ignore it and go right to this. Read this and absorb it. The function f is continuous on the closed interval -3 to 3. So since it is continuous, does that mean it's also differentiable? Oh no, we don't know that. Okay, so we got to be careful. All right, such that f of -3 is 4 and f of 3 is 1. That's cruel of Mr. Widmeyer. I know it's too early in the morning to be asking questions like that. All right, the function f prime and f double prime have the properties given in the table below. Okay, in fact, if we look at our table here, is f prime differentiable on the interval from -3 to 3? No, because we failed to exist at -1. Same thing with the second derivative. It fails to exist at -1 as well. And so, though they're not differentiable for the entire interval, right? Not differentiable for the entire interval here. Okay. Moving on here then. Letter A, at what value of x does f attain its relative minimum and maximum value, if any? All right, so let's again back up. What does it mean? What does it mean for a function, or how do we normally find when f attains a relative minimum or relative maximum? What do we normally look at when we want to determine if f has a relative min or max? First derivative. Okay, for a relative minimum, we want to see when the first derivative is changing from what to what? Negative to positive, and then for a relative maximum, we're looking for when the first derivative changes from positive to negative, okay? So negative to positive. I'm using these signs here. Do not ever use these in your actual explanation. Don't use the minus sign for the word negative. Don't use the plus sign for the word positive. You will not get credit for your justification if you do that. I'm doing it here just for some notes, okay? So let's look at our table here. Does our table indicate that f prime changes from negative to positive at some point? Does the derivative change from negative to positive at some point? No, it does not. So, no relative minimum. I don't know, I'm just sticking with the red here, I guess. Because f prime does not change from negative. I know it doesn't say justify, but I'm doing this because it's notes. So no relative minimum because f prime does not change from negative to positive. Okay, if it doesn't say justify, you don't need to justify, right? Okay. Is there a relative maximum here?
Yeah.
Yes, where? Well, wait a minute though. This is okay. At x equals -1, the derivative doesn't exist. Is that still a possible critical point? It doesn't equal 0 there. Yes, critical points still occur not only when the derivative is 0, but also where the derivative does not exist. So the x equals negative 1 is still a critical point. So yes, relative max at x equals negative 1 because f prime changes from positive to negative at this point. Okay. Okay. All right, the next question. Is f guaranteed a value of c? Aha, so we're talking about trying to show that something must exist. Is f guaranteed a value of c where negative 3 less than or equal to c less than or equal to 3 such that f of c is greater than or equal to f of x for any other like x value in that interval there? If so, find the value of x equals c if possible. Okay? This wording here, what is that equivalent to asking? Does f have an absolute what? Maximum. Okay? Does f have an absolute maximum? Okay? What theorem allows us to guarantee the existence of absolute extrema? Not the intermediate value theorem. Intermediate value theorem tells us things between must exist. We want extreme values to exist. The extreme value theorem on the very first page of these notes here. Okay? What must occur? Okay? There is guaranteed to be an absolute minimum and absolute maximum for f on a closed interval AB as long as f is continuous on the closed interval AB. Is our function continuous in the closed interval? It sure is. All right, so since f is continuous on negative 3 to 3, okay, then there is a c, negative 3 less than or equal to c less than or equal to 3, such that f of c is greater than or equal to f of x. Okay? If you want to name drop by the extreme value theorem, okay? You don't need to name drop it. If you show that the conditions are met and then you give the conclusion of the extreme value theorem, you don't need to then give it more, significance by saying by the extreme value theorem, okay? You've essentially stated the extreme value theorem without just using the words extreme value theorem, so that's okay. Okay, not necessary, but why not name drop? It's kind of fun sometimes, right? All right, so find the value then of x equals c if possible. Show the analysis that leads to your answer. Okay, so same kind of argumentation we've used in the past, right? What are our candidates for absolute extrema? Endpoints of the interval and critical numbers. Okay, so here we have four such numbers. Okay, we have x equals negative 3. Can x equal negative 3 be an absolute maximum? No, why not? F prime is positive immediately after negative 3, which means f is increasing. Okay? Okay, so x equals negative 3 is not because f prime is 0 after x equals negative 3. So f is increasing after x equals negative 3. Okay. The next place that we get to is x equals negative 1. Right? Next critical point we get to is x equals negative 1. Could x equals negative 1 be an absolute maximum? f prime is positive to the left and negative to the right, okay? And then further beyond that, still negative. So in fact, where is our absolute maximum located? At -1, okay? Okay, so I'll say the absolute maximum is at x equals -1 because f prime is positive to the left and negative or 0, right? Because at the instant of x equals 1, the derivative is 0. So negative or 0 to the right of x equals -1. So x equals 1 and x equals 3 will, I should say, I guess, so f of 1 and f of 3 will be lower than f of -1. Okay. These get really wordy, but you really got to show that you're considering all the possibilities and eliminating or choosing from those different possibilities there. Okay. Letter C. Find the x-coordinate of the point of inflection for the graph of f. Justify your answer. Okay. How do we normally find points of inflection for a function? What do? We look at the second derivative and see when the second derivative does what? Change from positive to negative or negative to positive. Okay? So, does our second derivative change from positive to negative or negative to positive? Yes? Where? At x equals 1 and x equals 1 alone. So, x equals 1 is a point of inflection of f because, oops, I don't know why I put a comma there. F prime prime changes from positive to negative at this point. Excuse me. That's all you need to say. Again, if you wanted to be like really thorough, you could say, therefore, f will be changing from concave up to concave down at this point. But not necessarily. This is sufficient. Okay. Let's take a look at example 7 here. Questions on any of that, I guess, before we move on? I know, like, shoving a bunch of information, but a lot of these questions are pretty similar. So, all right, let's take a look at example 7 here then. So, take a minute, consider that, give an answer. The graph of f prime is shown. Which of these is the graph of f? Okay. Which of those is the graph of f? If f prime is shown, okay. Look at where f prime is positive. F should be increasing. Look where f prime is negative. F should be decreasing. Locate relative extrema. Locate relative extrema, okay, as well. And also think about your concavity as well, too. Oof, I gotta think about this one myself. Let's see here. All right, what's the answer here? C. Let me ask you this. Okay, so f prime. Is f prime continuous? If f prime is continuous, then we can say that f is f then differentiable. Right? Does the derivative have any problems with it? No. So then f is differentiable, which if f is differentiable, that means f must also be what? Continuous, so can C be a possibility? No. No, because it's not continuous. So it's not C. Okay, it's not D either because it's also discontinuous. Okay, so A or B, it is A. Okay, so there it is. A, okay. Questions on why it is A? Okay. So we are running short on time here, but we'll keep going because we still have... No, we don't. We don't really have much time. It's not... Yeah, my clock, I still need to fix my clock. It's not really 9 at all. So, but what I would like you guys to do, there's homework posted to Google Classroom. If you would finish this up for homework 2, this last one here, okay, so there's homework posted to Google Classroom, but finish this up too. I won't check this, but we'll go over it in class tomorrow during homework time, okay? Yes, sir. So please give this a try. All right, and then we'll move into optimization tomorrow.
Do you know, when is the assembly supposed to start?
I'm guessing roughly at 10. I'm guessing the juniors are supposed to kind of make their way there, and then, you know.
Your second law class will
Yeah.
Mr. Whip. That's fun.
Yes.
For 6B, I'm solving all the work, but I don't really understand how this is asking for the maximum.
All right, one sec. Let me just finish this video here real quick.